All right, everybody, we'll go ahead and get started. I have posted the fourth and final practice exam on Learning Suite along with the key. All of it and the study guides for this section, I think, study guides 13, 14, and I think those are the pending ones, are due at the same time the practice exam is, I think, after the final, so we'll just kick everything down the road. The final exam will be given on April 16th and 17th, depending on which of the two sections or which of the two class times you're in. The scheduled time for the final will be different and on different days, so we're compromising by making it available on both of those days via Learning Suite, same rules as before, similar time limit. I've told people the final should be anywhere between 25 and 30 questions. Folks have asked, is there a percentage that will emphasize this last portion versus others? The answer is yes. The question, what is that percentage? I have no idea. I haven't written the exam yet, and so I could make one up. Somewhere between 10 and 50. I don't know. Is that terribly? Just don't even worry about it. It's not even useful to know. Yes, you can take that exam on either of the 2 days. The rules are, again, going to be open book, open notes. You can use the internet. You may not consult with another human about your answers. You may not check in with another human just to see before you press submit. Make sure all your answers are the same. That would count as cheating. Everybody knows that, but I just thought I'd say. Anything else? No, I don't think so. Had to speak in church yesterday. Our bishopric has, our former Relief Society president is now in charge of getting people to speak in sacrament meeting, which has been awesome because she's been able to get more women to speak. But we get a text last week, and my response was, she says, can you speak in church on Sunday? And I tried what I have learned from my children, which is new phone, who dis? But Amber said that was not as funny as I thought it was, I think. So we ended up speaking. I actually said some of the things I've talked to you guys about before. There were Star Wars references, though, and I got a text from my friend that said, Josh, Star Wars references, 2 or 3. Amber, Star Wars references, 0. Josh wins! Anyway, it was a lot of fun. Amber's talk was actually really good, too. 2, like mine, was really good. No, it wasn't, but Amber's was pretty good. We had to speak a couple years ago, and they made me go first. And for all that Amber and I had talked before about feminism and the importance of equality between men and women, I talked way too long, and she didn't have quite enough time to make her points because I spoke too long. And I felt really bad about that after the fact, sort of a hypocritical thing. So this time I timed myself and was very careful. Let me tell you, we were done with the talks in sacrament meeting after just a half hour after we started. It was fantastic. I hope we never go back to the old way. Anyway. All right. So NMR, we've talked about chemical shift, which tells you something about the environment a proton is in. We've talked about splitting, or coupling, which tells you what a proton is adjacent to. The patterns you're going to be looking for are what's going on there? The 1-to-1 doublet. That means you're next to 2 protons. The 1-to-2-to-1 triplet, which means you're next. Oh my goodness, already I'm getting things wrong. Don't write down what I say, just write down the things that are true. That's reassuring, isn't it? 1-to-1 doublet means you're next to 1 and only 1 proton. The 1-to-2-to-1 triplet means you're next to 2 protons. There's also the cousin of the 1-to-2-to-1 triplet, which is the 1-to-1-to-1-to-1 doublet of doublets. This is when you are next to two protons, but have different coupling constants with each one. Then the next is the 1 to 3 to 3 to 1 quartet, which means you're next to 3 protons. There are other more complicated patterns, but these are the most useful ones. And for those patterns, just consult Pascal's triangle. But that's what we're looking for. And this is where we get a lot of the connectivity information in organic molecules. In the quartet, are all 3 protons chemically identical? Yes, most of the time. Most of the time when you see a quartet, that means there's a methyl group adjacent to the peak that you're interested in. Recall that the splitting in the peak doesn't tell you how many protons are represented by that peak. It tells you how many protons are adjacent to the proton or protons represented by that peak. So where do we get the number of protons from? It turns out we get this from integrated peak area. So way back in calculus, you may have learned that you can calculate the area under a peak by making little parallelograms and then adding them all up. And we could still do that today with NMR structures, only why do for computers what they can do for themselves? So now when you see a peak in the NMR, you choose a cutoff on this side and a cutoff on that side, and then the program actually measures peak area and plots it over your peak like this, which is kind of fun because it looks like an integral. And the distance between these 2 points is related to the peak area. And so printed by each peak, once you set these cutoffs, is a number that is given in arbitrary, meaning meaningless, area units. Sometimes these are numbers that are greater than 1. Sometimes these are decimals. The number itself doesn't mean anything, but the ratio between numbers of within different peaks can tell you quite a bit. For example, imagine a spectrum, and we're just going to do singlets here. Oops. And I'll try to make it clear. This is peak area, not peak height. Peaks can vary in their broadness. To the extent that all peaks are similarly narrow, peak area will track with peak height, but it doesn't necessarily have to be that way. So imagine you have 2 peaks in an NMR spectrum, and you set the cutoffs and you integrate them. These are some fairly ugly looking peaks. And let's suppose we measure this peak area and the number turns out to be 0.48. Actually, let's not make it nice and even. Let's say 0.49. And then this one ends up being what am I even thinking about? 0.70. The relationship between these 2 numbers is the same as the relationship between the number of protons represented by peak B versus the number of protons represented by peak A. So how do you figure out how many protons each peak is represented by? Well, you kind of have to estimate and see whether it makes sense. Understanding that you can't have non-integer numbers of protons in a molecule. If your answer is, oh yes, this peak represents 2.46 protons, you're doing it wrong, because there's no such thing as 0.46 of a proton. So looking at this, what would we say? Well, Does it look like a 1-to-2 ratio? Start with a smaller one, call that 1. Is this a 1-to-2 ratio? No. If so, this would be more like 1 instead of 0.7. Okay. What other ratios are reasonable in organic molecules? Well, they could both represent 1 proton. That's clearly not the case. 1 could represent 2. It could be 1-to-3, but that's even worse than 1-to-2. All right, let's try some other ratios that would be common in organic molecules. 2-to-3. What do you think about that? Or, yeah? Anything else I was going to write, 2-to-2 would be the same as 1-to-1. Incidentally, you can't necessarily tell those two possibilities apart. Sometimes you need other information to tell those possibilities apart. But in this case, what we've got is close to a 2-to-3 ratio. You could use a calculator to do that, or you could sort of squint at it and say, well, that number is 0.49 is close to 0.48, meaning 1 proton would be around 0.24, and this number is close to 72, which would be 3 protons. Do you see the numbers aren't going to line up exactly, but they're going to be close enough to get an idea. Okay. So we're going to use integrated peak area to tell us how many protons each peak represents. Sometimes in your text with the problems that are given you, and actually I think on the practice exam I'm taking most of the problems straight out of the text, at least for the NMR problem. Sometimes they'll go easy on you and just say, hey, this peak represents 2 protons. Other times they'll show you numbers and you'll just have to figure it out. Understand the numbers don't mean anything other than they're proportional to peak area and proportional to number of protons represented by the peak. All right, you got chemical shift, you got connectivity through splitting, you got number of peaks. That's now going to be nearly enough information to solve the structure of molecules. Now we're going to start practicing NMR problems. Some of these will actually be from your practice exam and we'll do them together. Next time I'll try to bring some other ones as well. Typically in an NMR problem, you're going to be given a molecular formula. And there is some information you can extract from a molecular formula. I'll point out in chapter 3, I should have taken this out of the study guide. In chapter 13, rather, the text walks you through how you can take a number from mass spec and basically guess through trial and error and figure out sort of what a molecular formula might be. That's generally not a useful skill anymore. We have other techniques for assessing molecular formula of the molecule. Usually you have an idea of what it's going to be and you just use mass spec data to confirm that you did make the desired product. So I'm not going to be saying the peak in your mass spec is 97. What is the molecular formula? I don't find that to be a useful skill. However, given a molecular formula, there's actually some information you can get about how many pi bonds or rings a molecule must have. So let's compare the molecular formula for 1, 2, 3, 4, 5, 6 hexane versus cyclohexane versus hexene. 1, 2, 3, 4, 5, 6. All right. For cyclohexane, we would see that this is C6H14, I think. As a hydrocarbon, it follows the general rule of number of carbons and number of hydrogens, where N is number of carbons, the number of hydrogens must be 2N plus 2. That may be a Gen Chem thing for hydrocarbons. That's for a fully saturated hydrocarbon with no double bonds or rings. Now, if you look at the molecular formula for cyclohexane with just one ring, that's C6H12. So a ring accounts for the disappearance of 2 protons relative to a fully saturated hydrocarbon. That makes sense, right? Because you've got to pop off one of the protons on either of these methyl groups and then connect the 2 carbons together. But similarly, including one double bond, also accounts for 2 protons missing relative to what you would expect for a saturated hydrocarbon. So we can use this information to calculate something that is called degrees of unsaturation, or I prefer, but your text doesn't call this, double bond equivalence. That is number of pi bonds or rings. And for simple molecules like this, you're going to take 2 times the number of carbons plus 2. This is equal to the number of hydrogens expected in a saturated hydrocarbon. And then you're going to subtract the number of hydrogens you actually have, and then divide by 2, because each missing pair of protons accounts for either a double bond or a ring. So you can apply this formula to cyclohexane. 2 times 6 plus 2 is 14, minus 12 is 2, divided by 2 equals 1. There is 1 double bond equivalent in cyclohexane, which is why it's a ring. Similarly, we would make the same conclusion for hexene. If all we had was the molecular formula, we would not necessarily know whether it was cyclohexane or hexene, but we would know that you had to have one, no more than 1 double bond or ring, exactly 1 double bond or ring. With me so far? Now, what about heteroatoms? How do they affect this formula? Well, let's look at how incorporating an alcohol into a fully saturated hydrocarbon affects the formula. So let's make it easy. Let's do butane. That's C4H10. Butanol is C4H10O. Notice that when we incorporated the oxygen, we basically kept the proton. We just put the oxygen in between the carbon and the proton. So having an oxygen in a molecule without any double bonds or rings does nothing to the double bond equivalent. So you can ignore the number of oxygens in the molecular formula if you're calculating double bond equivalence. Same is true for sulfur, because it has a similar effect on the molecule as oxygen. Let's see. What about nitrogen, amino compounds? Well, let's again compare adding a fully saturated amino group, no double bonds or rings, versus butane. Every nitrogen we add introduces 1 more hydrogen in addition to what we used to have, right? It's not that we just insert a nitrogen in between this carbon and this hydrogen. Each nitrogen gets to be bonded to 3 things, so you need 1 extra hydrogen. To account for that, in our double bond equivalence, when we think about the number of hydrogens we expect in a saturated hydrocarbon, we're going to need to add to that the number of nitrogens. So our formula would be 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens you have divided by 2. And if you apply that formula to this molecular formula, if you apply this equation to that molecular formula, 2 times 4 is 8, plus 2 is 10, plus 1 is 11. But we have 11 protons. 11 minus 11 is 0, 0 double bond equivalence. By the way, if you come up with half integer values, you're doing it wrong, because there's no such thing as half of a double bond. Finally, what about the effect of adding a halide? This would be C4H9Cl. Adding a halide, because a halide can only be bonded to 1 thing, adding a halide totally replaces a hydrogen. So we're going to have to adjust our formula to subtract the number of halides. So we could adjust that 2C plus 2 plus the number of nitrogens minus the number of halides, where X is a halide, minus the number of hydrogens divided by 2. In this case, 2 times 4 is 8, plus 2 is 10, minus 1 for a halide is 9, minus the number of hydrogens we have is 0, 0 double bond equivalents. Okay? So this is a formula you can write down, you can apply, but you can use it to tell how many double bonds you have to have in a molecule based on its formula, and that's easy. All right. Any questions about that? So let's start in on a particular problem. I did this with some of you in office hours, but it's okay. We'll go ahead and get started. C4H8O2, this NMR spectrum, you see 3 different kinds of protons, 3 different peaks, and you're told the IR has a strong peak at 1700 wave number. So let's first start with the molecular formula and try to get as much information as we can. Let's calculate the double bond equivalents that this molecule has. How many pi bonds or rings must it have? 2 times the number of carbons plus 2. There's no nitrogens or halides, minus the number of hydrogens, which is 8, divided by 2. I get 1 pi bond or ring. I don't know which, but I know it's got to be one of those, because I've basically shown that there are 2 protons missing from what we would expect for a fully saturated hydrocarbon. Now, IR has a strong peak at 1700 wave number. You maybe haven't looked at that. You maybe haven't looked at an IR table for a while. But if you did, you would discover that sharp, strong peaks at 1700 wave number are characteristic of carbon-oxygen double bond, a carbonyl group. There is a particular place where a triple bond shows up. I just don't know where it is. Yeah. Okay, that's good because that actually accounts for our pi bond. So we're seeing some consistent information in the data. Usually the data you're given has more than enough information to give you the structure of the molecule, so usually you're going to find consistencies that tell you the same thing. In this case, the molecular formula told us there was 1 double bond, so did the IR, and the IR even said what the double bond was to, right? It's to an oxygen, between a carbon and an oxygen. One other thing we can get, we haven't seen the IR spectrum, but if there were a strong broad peak in the 3000 to 3500 wave number, that would be consistent with an alcohol or a carboxylic acid. But we don't see that here. There's no peak for an OH group. So we can use that to rule out the other possibilities. You've got 2 oxygens. We know one of them's involved in the double bond, but the other one, whatever it is, can't be an OH group, because otherwise that would have had to be listed there. Okay. And yeah, I'm not allowed to withhold information like that from you, right? You can use things, you can use the absence of an IR peak as evidence for, or evidence against a particular kind of group. All right, so we've already got one of the pieces of our molecules. Now we've got 3 different peaks. Sometimes I like to organize my thoughts with, for analyzing NMR data in a table. You certainly don't have to. But when I do this, I like to write in one column chemical shift. In another column, I like to write the number of adjacent protons, which we're going to get from splitting. And then in the last column, I like to write, I forget. Oh, sorry. In this column, I like to write number of protons represented by a peak. So basically, this could be like integrated peak area. And then over here, I like to write number of adjacent protons. So I'm going to get this from splitting. So the first peak I see, and I like to start with higher chemical shifts because usually those are more informative. Those are in unique situations. We see a peak at around 4 ppm. It has an integrated peak area of 23. I'm not sure how many protons that represents. I'm going to have to compare it to the other peaks. I see that it is a quartet. I'm going to use Q to abbreviate quartet, which means it is adjacent to how many protons? 3, right? Adjacent to 3, and at this stage I'm going to say most likely a CH3 group, right? That's one of the most common ways to be adjacent to 3 protons. At around 2 ppm, I see a peak that integrates for 29 arbitrary area units. Don't know how many yet, how many protons that represents, but I'm going to need to make some comparisons. I see that it is a singlet, which means it is adjacent to how many? 0 protons. I like the number 0. Sometimes when I'm teasing Adam, when he's complaining, I don't want to brush my teeth. He's almost 10. Come on, right? When you were 10, did you refuse to brush your teeth? In any case, he complains about that, and I say, Adam, guess how much I care? And the answer is 0 much. 0 is a great number. He's turned that one around on me again, though, so you got to be careful what you say to kids. All right, adjacent to 0 protons, the peak at 1.2 ppm integrates for 30 arbitrary area units and is a triplet, which means it's going to be adjacent to 2 protons. One way that you can be adjacent to 2 protons might be to be adjacent to a CH2 group. Okay, so let's deal with the integrated peak area. There's a couple of ways to do this. There's the hard way and the easy way. The hard way is to add up those 3 numbers and then divide that number by the number of protons in your molecular formula, and then you come up with some number for how many arbitrary peak area units. Arbitrary peak area units. We have an opportunity for an interesting acronym here, I'm not sure, but per proton. And then you go through and say, well, 23 divided by 10.2 is some number that's somewhere between 1.9 and 2.1, but I know I can't have 2.1 protons, so most likely 2. 29 divided by 10.2 is close to 3, so most likely 3 protons. 30 divided by 10.2 is close to 3, therefore 3 protons. So you can do it that way. That way only works, though, if you're convinced that your molecule is pure and the only peaks you're seeing are from protons in your molecule. Great to assume for problems from your text. Not so great to assume for molecules you actually made and purified, because most of the time they're not 100% pure the first time you try to purify it. So that's one strategy. The other strategy is just to test out ratios like we talked about earlier. So does this look like a 1 to 2 ratio? Probably not. It's more like 1 to 1.5. So let's try 1 to 3. Definitely not. 2 to 3, okay, close. Have to round down. We're looking at only one significant figure here, right? And so we would conclude that the peak at 4 ppm probably represents 2 protons. The one at 2 represents 3, and the one at 1 represents 3. See how we made that conclusion? Maybe it seems elementary to you, though I've found before that students tend to panic when they see numbers and don't know what to do with them. You're just looking for general ratios. So test 1 to 1, 1 to 2, 1 to 3, 2 to 3. those are sort of the more useful ones. If you think about common hydrocarbon functional groups, protons come in groups of 3, 2, or 1 usually. Okay? Questions about how we made those conclusions? No? Okay. So now we can start to generate some hypotheses about what each of these peaks represent. I'm going to label the peaks with letters A, B, and C. Peak A integrates for 2 protons, so that is probably a CH2 group. And I said it was most likely adjacent to a methyl group, right? Because it's a quartet. Peak B, I'm not sure what it's adjacent to, but I know that there are no protons on the thing that it's adjacent to. Peak C looks like a CH3 group that is adjacent to a CH2 group. Now, you should look at these 2 entries and see that they confirm each other's presence. A is a quartet, meaning it's adjacent to a methyl group. C is a triplet, meaning it's adjacent to a CH2 group. So you're getting the same kind of information here, which is matching what one peak is telling you is matching what the other told you. I'm not sure I said that well, so questions? If you could go in and measure those coupling constants, you would see that the coupling constant between A and C is exactly equal to the coupling constant between C and A. It has to be. And that's another way you can tell that 2 sets of peaks are coupled with each other. DBE stands for double bond equivalence. That's this stuff up here, or degrees of unsaturation. There's a question. I'm not, Thomas, maybe you rephrase. I'm not sure I understand. When I say adjacent, I mean 3 bonds away. So the methyl group protons are adjacent to the CH2 group protons. Okay, so I've got some pieces. Now I need to put them together. The pieces I have are an ethyl group. I have a methyl group that can't be next to a proton. I have a carbonyl group from our double bond equivalent analysis and from the IR, and then I have an oxygen that I haven't accounted for. So we can try to reason through what it would have to be, or we can just come up with some hypotheses and see if the hypothesis is consistent with the data. Sometimes students are afraid to try things because they think that by trying it, they're committing to something. Don't be afraid to draw something that turns out to be completely bogus. Actually, by analyzing whether your hypothesis is correct or not, you're going to learn a lot and you'll be able to check your wrong answer. So how could we put these together? Well, what if I had an ethyl group next to the carbon and then a methyl group here? What's wrong with that? Well, I forgot the oxygen, so that's not going to work. Though it would explain the CH2 adjacent to the methyl, and it would explain this methyl, which is not adjacent to any protons. So I got to get an oxygen in there. So one possibility would be this one. I suppose another possibility would be this one. Now let's take possibility 1 and check and see if it's consistent with the data. Methyl group, not adjacent to any other protons, so we would predict this to be a singlet. Do we see a singlet in our spectrum? Yes, we do. Okay, so far so good. Let's think about chemical shift. Those CH3 protons are adjacent to an oxygen. So if you go back to a chemical shift table in your text or in your notes, you would be able to find what to expect for protons that are adjacent to an oxygen. Anybody remember off the top of your head, being adjacent to an oxygen should do what? Should it make you shielded, or, yeah, Lauren? Deshielded, right, relative to being just a regular hydrocarbon. And you would expect a chemical shift for that methyl group to be in the around 3 to 4 ppm region. You could find that out from your NMR table. Is that consistent with the data for the singlet methyl group? No, in fact, that singlet methyl group shows up at 2. That's not anywhere close. We do see a peak at 3 to 4 ppm, but it's not the methyl group. So with that piece of information alone, we can put the big X of doom over that possibility. Let's try this one now, starting with the methyl group. It's a singlet. For being adjacent to a carbonyl, we would expect a chemical shift of around 1.5 to 2 ppm. That is indeed what we observe. For a CH2 group adjacent to an oxygen, we would expect chemical shift of around 3 to 4 ppm. That is indeed what we observe. And let's check connectivity. We expect the CH2 group to be a quartet. Yes, it is. Methyl group to be a triplet. Yes. And another methyl group to be a singlet. All of the data are matching this possibility too. So we can be confident that we got the right thing. Finally, we check the molecular formula of what we've drawn to make sure it matches this. And we check the IR data to make sure that it's consistent. Right? So you're not done when you write out the possibilities. You've got to go back and compare to the data to see whether your possibility is consistent. So can somebody screenshot it or find the page number where the ppm values are coming from? It's in chapter 14. I leave it to you to find it. But it's not hard. Okay, questions about how we went through that? So actually, problem F is kind of interesting because it's exactly the same molecular formula, and it also has a peak, a strong peak in the IR at 1700 wave number. If we did the double bond equivalent analysis here, we would discover that there must be either one pi bond or ring based on that molecular formula. We see roughly a 2 to 3 to 3 relationship, but unfortunately they're all singlets. Okay, so if we write out our table of chemical shift values and peak area and splitting, you've got a peak at 2, a peak at 3.4, and a peak at 4. And peak area is 31, 30, and 18. We've said likely this means 3 protons, 3 protons, and 2 protons. But the splitting is they are all singlets, so that means next to 0 protons all the way down. You've got pieces now. You have a CH3 group, a different CH3 group, a CH2 group, a carbonyl group, and an oxygen. And we got to figure out a way to put them together where these 3 groups are not adjacent to each other. So now you just try some possibilities. Try to come up with some things. So suppose I get started and I think, well, what if my methyl group is adjacent to a CH2 group? Otherwise, it would be a triplet, and it's not. So, okay. What could a methyl group be adjacent to here that is not, that does not have protons on it? Well, you got your carbonyl group and your oxygen. So let's try an oxygen. If the methyl group were adjacent to an oxygen, where would that show up? In the 3 to 4 ppm region. Do we have a peak there? Yeah? So, okay, so far so good. What if we put the carbonyl here? What's the problem with that? If we take out a methyl group, carbonyl, and oxygen, all we've got left is methyl and CH2, meaning they'd have to be adjacent to each other, which we've already said is not going to be possible because we only have singlets. So that carbonyl group cannot be attached to the oxygen. Instead, what looks reasonable might be to try, well, if I try the methyl group, that's bad because I just ended the molecule and I haven't accounted for the other things. So what if instead of the carbonyl or a methyl group, I try CH2 here? CH2 adjacent to an oxygen, but not adjacent to any other kind of proton, show up in the 3 to 4 ppm region. Okay. Then I suppose to keep that CH2 group apart from any other protons, we'd have to put the carbonyl here and the other methyl group there. So now let's compare what we have proposed versus what we observe. This methyl group would be a singlet. We'll call this C, B, and A. Methyl group would be a singlet. It should show up around 1.5 to 2 ppm. We in fact see that oh, they've written the letters for us. How nice of them. C. CH2 group adjacent to both an OA oxygen and a carbonyl. Being adjacent to an oxygen should shift the the CH2 into the 3 to 4 ppm region. Being adjacent to a carbonyl might pull it even further downfield than that. We do see a CH2 group that is at a fairly high chemical shift, so that's consistent with the data. And then finally, methyl group CH2-3 adjacent to an oxygen. Yeah, okay. This is the answer, and it is the only answer that explains the data. All right. So you're solving a puzzle, kind of like Sudoku. You're going to have pieces of information that are confirmed in multiple ways, and you always have to compare your answer to make sure you didn't actually put 2 9s in that row. Wait, what are we talking about? Not Sudoku, NMR. Okay. Questions so far? All right. Let's try another one. This one has a nitrogen in it. So take a second and calculate the double bond equivalents that should be present in that molecule. And I'm getting real informal as the semester's going on. I'm now coming to school in my Star Wars t-shirt, so whatever. Go ahead and calculate double bond equivalents. Don't forget how to do the nitrogen. All right, you got the arithmetic cranking. You got an answer yet? How many? 4. That's right. There are 4 double bond equivalents, 4 degrees of unsaturation, 4 pi bonds or rings. Now, it's pretty tough to see how you would get 4 pi bonds in a molecule with 8 carbons, unless you've got a benzene ring. anytime the number of double bond equivalents is greater than is 4 or greater, you should be looking for additional evidence of a benzene ring. And in fact, we see that right away in the NMR spectrum. We see peaks that are in the region that's consistent with being attached to a benzene ring. So even without knowing anything else, the fact that I see 4 pi bonds or rings could indicate a benzene ring. A benzene ring takes care of all 4 of those degrees of unsaturation. Pi bond, 3 pi bonds, 1 ring, 4 double bond equivalents. So right away I'm thinking of this. Now, in the IR, they're giving me a bunch of numbers without telling me anything about the peaks. That's, I won't do that to you, but in this case it's pure distraction. You're not meant to get anything out of that. It's just meant to overwhelm you. So sidestep that and move on. Fortunately here they've given you, they've solved the peak area problem for you and just told you however many protons each set of peaks represents. So that's useful. So let's start to fill out our table. Chemical shift, number of protons, and splitting. We're going to start with this weird set of peaks in the 7 to 7.5 region. Your text talks about peak splitting in benzene rings. In many cases, it is too complicated to analyze. And in some cases, you don't actually need to analyze it. And this is one of those cases. You're told that there are 5 protons. You've got multiple sets of peaks, and the splitting is weird, suggesting that those 5 protons are not identical. That's fine. They shouldn't be identical if they're on a benzene ring and there's other things on the benzene ring. But the fact that there are 5 of them, the only thing that could possibly be is a mono-substituted benzene ring. That's it. And because of that, I don't care which of this messy group of peaks represents which proton. You can figure it out if you want and come up with a hypothesis, but in many cases, this will be complicated enough that you can't interpret the splitting directly. But in this case, we're going to shrug our shoulders and say, who cares? We already know what those peaks represent. Do you see how we got to that conclusion? The fact that it was in the region consistent with being bonded to a benzene ring and that set of peaks represented 5 protons tells us everything we need to know. If it were 4 protons, we'd have to worry because then, right, there are multiple ways to put 4 protons on a benzene ring. It could be like this, or instead the other group could be here, or instead the other group could be there. There are other ways of interpreting, and usually the splitting patterns would be easier to interpret in those cases. But with 5 protons, it's simple. It's just a mono-substituted benzene ring. All right, let's look at the other peaks at around 3 ppm. We have 2 protons, and it looks like a triplet. In office hours today, somebody noticed that this, I think it was you, Matthew, noticed that this peak is not a really symmetrical 1 to 2 to 1 triplet. In fact, you sort of have to squint and tilt sideways. It's okay if the ratios aren't perfect. There's really nothing else that could be than a triplet. We'll use the abbreviation T for triplet. The fact that one side is higher than the other here, there is a phenomenon that explains that, but I don't understand it, and you don't actually need to know it to interpret these data. So that triplet should mean that this group is adjacent to 2 hydrogens. All right, we'll have to leave it there because we're out of time. We'll pick up with that when we begin next time. We'll just continue solving these problems, working on them. And that'll be the final lecture in OChem. You've come to the end.